Hi, this is AP Calculus section 5.2, and we're going to start doing the natural log integration. We did some derivatives with the natural log in the last section, and now we're just going to go and do the reverse for the integration. We have to separate out in our minds the differences between a lot of these different integrals and also understand the rules of logarithms. So I got a big warm-up for you to try. And most of these are regarding older problems that you've done before, but I want you to try most of these. This number 8 might be a little tricky for you, but the rest of them you should be okay to do. So go ahead and start that, and then I'll come back with the solutions and talk about them. So pause. Okay, for this first one, you had to do a u substitution, so you had to let u equal this inside function, and then take the derivative of that, so you get 5. You got to put the 5 in. You can't just put 5 in without balancing it off. You can't change this whole thing, so we just take 1/5 of 5, and then they take the antiderivative of the sine of u, which is the negative cosine. So we get this value here. This one we let u equal to the sine of x. That's raised to the third, so we get u raised to the third. Du is equal to cosine dx. I should have dx written there. And then this is to the 1 higher power, divided by 4. And so I replace the sine x, and I get this here. If you're unfamiliar with the u substitution, go back and check out the u substitution video. This one gets a little bit trickier. What you try to do a lot of times with these logarithms is split them up with the logarithmic rules before you do take the derivative. However, there is no logarithmic rule for this log of a sum. And so what I have to do is I have to take the derivative is 1 divided by whatever's inside the log function. So I have that here. And then you have to chain off the derivative of what this thing is. And so I got times the sum, so I got in parentheses 1 plus, and then this one right here, you have to go ahead and figure out the derivative. And you can just get x over the square root of 4 plus x squared. Now when you multiply these things, some of the things cancel out. I got a common denominator here, so I turn this 1 into square root of 4 plus x squared. And so I get this whole thing becomes this, and then we can cancel off this whole part. These should be grouped in parentheses. I don't have that written, but you should have them grouped in parentheses, so I'm left with 1 over the square root of 1 plus 4, 1 over the square root of 4 plus x squared. Remember that you can well, yes, we're okay with that. So these are derivatives. Now, when you did the true-false ones, most of these are false because these are common errors that students make. So if you look at A, there is no rule for the log of a sum. This is wrong. So this whole part here, I don't like. So that should be gone. For this second one, then we have the natural log. We can take the natural log of x to the 4 divided by, oh, what's wrong with this one? Well, what happens is that you do a log of the top, the numerator, minus the log of the denominator. So there should be a subtraction symbol in between these rather than division. So don't do that. Don't do what I have written here. So that's false. Part C, if you take the derivative of ln of pi, well, pi is a constant, so ln of pi is also a constant, so this actually would be 0. Then if we do this one, it's 1 over 3x, but what was forgotten? Well, you have to chain off the derivative of the denominator and multiply it by 3. So actually this becomes 1 over 3, as we did in last notes. This one here, if we integrate 1 over x, we learned this last time, this is ln x. And to satisfy our domain issues, this has to be the absolute value of x. I didn't have that written in there, but you should put that in there, plus c. So that one's true. And don't do it the wrong way. This is common too. So you got to make sure that you know which way you're going. Derivative ln x is 1 over x, but the antiderivative is not 1 over x. Now these next ones, why I put these in here is because they look like natural log functions, or they might turn into natural log functions, but they actually don't. Don't forget your previous rules that you've done. So for this number 5 here, what we do is a rewrite. So this would be x to the negative 2. You raise it to the 1 higher power, divide by -1, and then you get plus c, and so you end up with this right here. This has nothing to do with the natural logarithm. This next one you can do a u substitution. U is equal to x squared plus 1. Du is equal to 2x. I need a 2. Balance it off with a 1/2. There's my 1/2. So I'm left with 1 over u cubed. Rewrite. And then we can figure this out. I got a lot of scribbles there, but that should be the right answer. Then number 7, we do what I call the rabbit method. The rabbit method is where I take the denominator and I take the pieces of the denominator and I move them together with the numerator. So what I draw is the rabbit. So what's the square root of x divided by x? That's my 1. And then what is 1 divided by the square root of x? X to the -1/2. And this should be in parentheses technically. And then I just do it piece by piece, the antiderivatives, and this is what I get. Number 8 then I said was a little bit different. If you do let u equal to x squared plus 3x, du is equal to the denominator with the dx there. So I get 1 over u du. Well, we figured out that this is the natural log. And also, if I do the rewrite on this, if this is u to the -1 du, if I say raise to the 1 higher power, oh, that'd be u to the 0 divided by 0. U to the 0 divided by 0, well, that does not fit our particular rules. When we're doing these antiderivatives, we can't let this exponent be -1. The antiderivative of this, whenever you get this nonsensical thing, that should be telling you, oh, that's the one that's a little bit different. That would be the ln, natural log of the absolute value of u plus c. So then I put this back in. So what's going to happen in today's lesson, whenever we see a function in the denominator, its derivative in the numerator, we can just get ln of the denominator and go with it. But don't go back to some of these other ones and mess them up. Okay, so here's some rules. The integral of 1 over x dx, so the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. If I do it in more general terms, and u is a function of x, and you see in the denominator the function, and the numerator its derivative, then you just get the ln of the absolute value of the denominator. Okay? So let's try some of these. Well, this one is the 4 is just a constant. It can go along for the ride. So this just would be 4 ln x. This one, we do have to do a u substitution. And so u is equal to 3 dx. I don't have the 3, so I need to put it in and then balance it off. So this is just going to be 1/3 the integral of 1 over u du, which is 1/3 ln of u, absolute value, but this is u, so I'm going to shortcut this, 3x plus 2 plus c. This one here, some people like to try to put u equal to the sine of x, and then there's du. The problem is that we can't put du in the denominator, and we can't do a perfect substitution this way either. So we usually have to let u equal to the stuff in the denominator, and then try to balance it off with what's in the numerator. So the derivative of the cosine is negative sine, theta d theta. And so here's my d theta, and here's my cosine. So this just would be the integral. Oops, I need a negative. So don't forget that. So this would be 1 over u du, which is equal to negative ln of u, which is negative ln of the cosine. So I did my back substitution there. All right. And what will happen is that sometimes you'll see this function here, and you might take the derivative of it. Well, if I take the derivative of it, you can check to see that you get back to here. I think that's always a good way to go. Whenever you're doing this integration, take the derivative to make sure that things are working out properly. The next one here, this is a definite integral. If I let u equal to x squared plus 3, people have trouble balancing this when I need the 2. A couple different ways to do it. You can bring out the 4, put in the 2, and put in the 1/2. Or you can just figure out which products do you need to make 4 such that you leave a 2 on the inside. That's what I'm going to do. I don't know if that made sense or not, but I'll show you. I need the 2. But I originally had 4. I can't change my original integral, so I still need 4. Well, 2 times 2 is 4. So that is a different way to do it. And then if I do the substitution, I got 2, and my integral is now in terms of u. So it'd be 1 over u du. So I get 2 ln of u, which is just my x squared plus 3. This is a definite integral. I got to use my x limits again. So this would be 0 to 3. So I get 2, and then plug those in. So if I plug in the 3, I get 9 plus 3, which is 12. And then if I plug in the 0, I don't get 0, I get 3, minus 2 ln 3. Now if you look at this, we can probably simplify this a little bit with our rules of logarithms. I can take the squared and put it up above both, or I can factor it out. Why don't I factor it out? And then I can take 12 divided by 3. Because the log difference is the log of a quotient. So this would just be 2 ln of 4, and I can take this and put it up on top, and so this is ln of 16. You can get an approximation for that by typing that into your calculator. All right, now this one, do you see a function and its derivative? Maybe pause and try this if you see that. But I see this, u is equal to, I'm going to let u equal the denominator, and du is equal to 1, and the derivative cosine is negative sine. And so I see a function and its derivative, almost. So what has to happen is that I need a 1 minus sine of theta here, which in other words, I multiplied this numerator by negative 1. And so I need a negative out in front. Oh, I just crossed off the wrong one. Now I'm going to shortcut this process a little bit by saying, okay, do you see a function and its derivative? Yeah, here's the function, here's its derivative. Function in the denominator, derivative in the numerator. That means that my antiderivative will be the ln of the denominator. And it's indefinite, so I put a plus c. So that's kind of a shortcut way that you can start looking at these if you wish. And that's using our rules that we have right here. Function, derivative, ln of the denominator. Okay? So that is a way to shortcut that a little bit. Keep on rocking here. Why don't you try some of these? And some of them will deal with ln and some of them won't. So be careful. And when you rewrite, it's got to be a 1 over u situation in the integral. So pause and try these, and then I'll come up with some of these solutions for you. So if I look at this first one, I'd let u equal to what I have inside the square root in the denominator. And so if I do my u substitution, I need a 4, put it in, balance it. There's my balance. But then I end up with u to the negative 1/2. This is not u to the negative 1. That would be giving me my natural log. This rule right here, I can use the power rule. The power rule for integration, which means raise it to the 1 higher power and then divide by whatever I have there, which would be, in this case, the 2. Dividing by 1/2 is multiplied by 2. So I get 1/2 out in front. There's my u. I back substitute that in. And then I got the 1/2 for the exponent, which is the same thing as square root. So there we go. We did not use ln here. I cannot emphasize that enough. Even though it's on the ln page, these things will be mixed up a little bit. Looking at the next one, with this, well, first of all, the degree is 1 higher in the denominator. So if I let u equal to x to the 5th, du would be equal to 5x to the 4th. Well, I could maybe make that work, but really this doesn't work in the present way that it is. So what I have to do then is I have to do the rabbit method. So I do this. So I get x to the 4th over x to the 5th. That's correct. And then 2x to the negative 5th. This one I can use the power rule. This one I just take the antiderivative 1 over x and I get ln x. And so it's ln absolute value of x, and then this antiderivative, and then simplify with no negative exponents. Remember, no negative exponents in the answer. You can have rational exponents, but not negative. If you look at this next one, number 8, hopefully you didn't try that one too much. But it's not possible with our present methods, because if I let u equal to the denominator, oh, no good. If I let u equal to the numerator, for instance, this would be 4x to the third. Well, I'd have to put, this just doesn't work because I'm going to end up with the du in the denominator, and that would be split, and it just doesn't work. Okay? I don't know how to do that one offhand right now, but maybe someday I'll figure that one out. Okay, if we look at this next one, do you see a function as derivative? Sure. 14 plus tangent of x is a function. Its derivative is secant squared. Function in the denominator, derivative in the numerator. Boom. Done. It's just the ln of what we have there. Number 10 is tricky. I sure hope you tried this one. If you didn't, pause this and don't look at this and try it. Back? Okay, I hope you are. So now if we let u, I do see a function as derivative, but this doesn't seem like it's going to work out. I see the function as being ln x and its derivative being 1 over x. So, well, let's try it. The worst thing you can do is just sit there and look at it and not do anything. So I'm going to let u equal to ln x. Du is equal to 1 over x. There's my 1 over x right there. Oh, okay. So if I put that together with this dx, that is, I need to put that in. I don't know why I haven't been. But the du just replaces all that out that I had in the red there. And then all I'm left with is the u in the denominator. So I get 1 over u, and so ln of x. Boom. Nice. Okay. So that's using the techniques. You also will have to do other u substitutions and stuff with the ln x, but just pay close attention and look for a derivative in the denominator. I'd said that wrong. A function in the denominator and its derivative in the numerator. Then you can do the ln. If not, you got to go back to our old, usually it's power rule stuff that we're dealing with. Moving on to number 11. Solve the differential equation. When we solve the differential equation, what usually happens is that we need to find the particular solution. When it says particular solution, find my function plus c. You got to go ahead and find the plus c. So if I set this up, it's not in differential form yet. So I'm going to take this dx and put it over on the other side. So I get 1 over x plus 1 dx. Then what I can do is integrate both sides. The antiderivative of 1 dy is y. And then this one here, well, I can do a u substitution. Some of you can do this without a u substitution. So you get 1 dx, and so my substitution, this just would be 1 over u du. So for overall, this is just going to be my natural log of u. So I'm going to end up with, I'm going to put it way over here, y is equal to ln x plus 1 plus c. Don't forget your plus c. This is called the general solution again. To get my particular solution, I need to use my initial value. So ln 6 is equal to ln of x, which would be 2 plus 1. I don't have to worry about the absolute value with a 3, plus c. Now here comes our logarithmic rules again. This is ln 3, so I'm going to put this all on the other side. So I'm going to get ln 6 minus ln 3 is equal to c. Log minus log, oh, that's right. That's going to be 6 divided by 3. So overall, c is going to be equal to ln of 2. This is not my particular solution yet. What I have to do is go ahead and plug in the c over here. And so in the end, I'm going to get y equals ln of x plus 1, absolute value, and then plus ln 2.
Could you put these together with a product? Sure, that would work as well. So sometimes you see that. So this might be ln of 2x plus 2, which would be all inside. Okay, the next one says find the average value of the tangent on the closed interval here. So I'm going to do average value, which would be this thing right here. And when I do this, this would be 1 over pi over 4 minus 0, 0 to pi over 4 of the tangent of x. So why I'm doing this problem is because I want to find the antiderivative of the tangent of x. Now if you notice, way up above in our previous stuff, I've already done this. And so if you look at number 3 during some of the initial problems, I had sine over cosine, which is the same thing as the tangent. So I let u equal to the denominator, and du is equal to the numerator along with the balancing of the negative. And so I get negative ln, or this thing right here, right? And so I can, since I know that rule, I can just go ahead and do that. But if you forget the rule, write it over into sine and cosine and work it out. That's the same thing that we do if we forget the rule for the tangent when we take the derivative. So over here now, this is going to be equal. I have the antiderivative of the tangent, which is the natural log of the cosine, but it's negative. And then I'm evaluating that from 0 to pi over 4. 1 over pi over 4 became 4 over pi. So this would be negative 4 over pi, negative coming from here. And then I have ln, plug in pi over 4 into the cosine. And the cosine of pi over 4 is square root of 2 over 2. Then I plug in the cosine of 0. Cosine of 0 is 1. So if I take ln of 1 over that, all that's 0. So this second piece just wipes out. And so I'm just left with negative 4 over pi ln square root of 2. All right, so that gives me a good idea of what we've been doing. And with the antiderivative of 1 over u du. And that tells us a lot about how to do these different situations when we haven't been able to do them before. Don't forget all your other power rules, though, and I would say that that's probably one of the key points, and you list a couple other key points when we're doing this. All right, thank you very much, and I hope you have a good day.